Okay, segment 2 of gas laws. Now, I forgot to mention the first time, and I probably won't mention it again, so you need to keep your head on straight on this. You should have gone to whatever textbook you bought and turned to the section on gas laws and kind of follow me and follow what they present in their presentation in between the two, gain some insight. After all, this total purpose is to clarify things for you and allow you to have better success. Okay, excuse me. Today, for section 2, we are going to talk about ideal gas. The ideal gas law is PV equals nRT. Pressure, obviously, is in atmospheres, volumes in liters. Little n always indicates number of moles. R is 0.08206 universal gas constant, liter atmospheres over moles Kelvin. And the temperature is in Kelvin. So we will probably always convert the temperature given in centigrade or Fahrenheit to Kelvin. And I'll throw a problem at you here. You have hydrogen gas, and you have 8.56 liters of it at 0 degrees centigrade and 1.5 atmospheres. What's the number of molecules? Well, you realign your gas constant formula, solve for N, and that means PV over RT. Well, pressure given as 1.5 atmospheres, 8.56 liters. Gas constant is 0.08206 liter atmospheres over moles Kelvin, and 0 degrees centigrade is 273 Kelvin. And if you can multiply and divide with your trusty little calculator, you come up with 0.57 moles. Multiply that by 6.022 times 10 to the 23rd, and it'll give you the number of molecules, because remember, this is a diatomic gas, hydrogen, molecules of hydrogen gas. All the problems about this are similar. They're not enormously difficult. A couple little additives. Density is always indicated as D, and it's mass over volume. Molar mass is equal to density times universal gas constant times temperature in Kelvin divided by pressure. You might want to try, start writing some of this down as you go through. Cards are effective. Paper, pencil. Typing it out. I'm sure some of the behavioral scientists will disagree with me, but the automatic activity of typing this stuff out on a laptop versus actually the process of writing it out is a different concentration level. That's the reason the downfall of school systems in general was the removal of cursive as being a mandatory action for the younger age brackets. The knowledge of cursive is not particularly useful, but the concentration needed to teach yourself cursive was very useful from a psychological perspective of concentration. Now, I'm sure all the psychologists and educational hierarchy will totally disagree with me, but I'm sorry, I raised 5 kids and helped raise 12 grandkids and thousands of other students in various levels of education. And I've seen this. And what I'm saying is actually quite true. So anyway, enough of my sermonette for the day. Next, we have Dalton's law of partial pressure, which says no more complicated than the pressure total is equal to the sum of the pressures, however they may be. Now, that sounds almost ridiculous, but it can be carried out almost to infinity. So that's the reason it's given. Okay, next on the agenda, kinetic molecular theory. See, I've written it at least small enough. Let's see if I can. All right, we'll go through it. Kinetic molecular theory. Number one, particles of gases are so small that individually we will equivocate them having a volume of 0. So again, number one, individual gas particles are given a volume of 0. 2, the particles are in constant motion. And because they're in constant motion, they're constantly banging off the side of whatever container they're in. If that's accepted as the pressure of the gas naturally. Number 3, gas particles have little or no force interaction on each other. Now, the old ping pong ball or the old, the reason this is important, that if in every intersection of a gas molecule or atom bouncing off the other one, there was a net loss of energy, you would have eventually a change of the energy within the system. So for this ideal gas to work, we assume that the interaction of the gases is like rubber balls or ping pong balls or golf balls bouncing off each other, negligible. And fourth, the average kinetic energy of a gas particle is directly proportional to the Kelvin temperature. Directly proportional to the Kelvin temperature. Thus, kinetic energy average is 3/2 of universal gas constant 0.08206 liter atmospheres divided by moles Kelvin times temperature. That is the basic theory for average kinetic energy of gases. Diffusion is, by definition, the mixing of gases. Effusion, however, is gases dispersed through a tiny orifice or tiny hole, if you want. Now, Graham's law deals with this effusion thing. He says is the rate of effusion of gas 1 over the rate of effusion of gas 2 is equal to the square root of the molecular mass of the second gas divided by the square root of the molecular mass of the first gas. Now, Graham's law is quite a big deal when you're talking about gases in motion, and rates. So, kind of, again, the older textbooks gave a great deal of detailed mathematical explanations, much more than you actually need to know, because quite often it delved into calculus. The older books have some of these things have differential equations involved. None of that is actually important to a general chemistry student. This is a survey course. So just knowing that it exists is the important factor. And I hope this was helpful.